Hello, how are y'all?
Hello, good and yourself?
Oh yeah, doing really well. You could tell Morro Bay's in the background, so can't complain about that. But I'm actually not in California right now, so that's fun.
Oh,
My
how
Zoom background
fun.
is. So let's think. We have started the recording going, and I'm going to do the typical share screen, and we'll see what happens in class today. Wanted to mention, just to start, that as a group, I think you did pretty well on the first exam. So I'm not surprised because summer students tend to be, especially in Stat 313, really solid. So we're happy about that. Second thing I want to mention is I don't think that I've put the answers for the first exam online just yet. I will be doing that probably soon, before my next class later today. So I wanted to mention the so sample ex not sample, but the actual exam answers should be online by an hour or two from now. Then I want to mention that because of things that are outside of this class, but related to my other class, this week, office hours on Monday and Wednesday will be shifted from the regular time slots a little bit. Right after our class today, yeah, Monday, 1:10 to 1:35, just like normal, we're going to have office hours, but we're going to shift the afternoon office hours forward by an hour, 2:25 to 2:50 p.m. Instead of the regular 3:25 to 3:50 p.m. on Monday. If that doesn't work for you, send me an email. We'll work it out. We'll figure out some other time. Wednesday, office hours will be 1:10 till 2 o'clock on the nose. Again, starting like right after this class, but going for a full hour. And then the later in the day, office hours on Wednesday will be changed up. So that's your announcement about office hours. I think I sort of sent you an announcement about that. I think that's what they're called inside Canvas, announcements. But you should have access to that information already. I just wanted to sort of be saying it verbally. So, again, good exams. I'll put the answers online. Those were the administrative things I want to be sure to mention to you all before moving forward at all. Do any of you have administrative questions that you'd like to ask right away? I'm not hearing any questions, and I'm not seeing any of you on mute. So that's a sign of some sort. What we're doing today is moving into, chapter five, and then tomorrow, chapter six. And just to give you some context, chapters, I guess, 0, 1, 2, and 3 are on the first exam. Chapter 4, sequential versus adjusted sums of squares. And then chapter 5, design of experiments. And then 6 are the beginning of the material that's going to be on the second exam. Chapter 7 is the last of the content on the second exam. So we're getting close to done with all that. And we should be finished up by later this week with the content for the second exam. So I guess if I look here on the syllabus, it'll tell us when that second exam is and how close I am to remembering the dates and times of things. Yeah, we're gonna finish up material. Oh, sorry. We're gonna have the partial F test a week from today, also as content for the second exam. So second exam is exactly 2 weeks after the first one, but it's all newish content, things that you hadn't seen in that prior stat class. Okay, so with that in mind, I'm still sharing a screen, but I'm not displaying what I need to see myself. Okay, so this is fun. Um, mhm. I completely lost the screen I need to see. Okay, so I'm gonna do this and that. Okay, so excellent. And now I'm gonna do this so I can do that. When you're working at one small laptop and that's all you got, it's a challenge. Okay, so last time, what we did with the multiple experimental variables, we talked about, or explanatory variables, we talked about adjusted and sequential sums of squares. And do any of you have questions about that content now that you sort of finished up the lab and turned it in? Okay, cool, cool. So let's dive into something new. And again, in each of these little sections, I try and sort of say, here's what to read today, chapter 5, on Tuesday, chapter 6. If you're the sort that likes to sort of take notes on a PDF, that's what we're doing today. Tomorrow, it's going to be that guy. I will be putting up a video later, right here, that's of me doing this right now. But if you wanted to watch from past summers, because cross-referencing in your group, one person could watch the 2023 content, someone could do the 2024 content, someone could do the 2025 content. That's actually a pretty good way of making sure that you sort of see and hear slightly different versions of the same thing that highlight, based on student questions, different aspects of the course material. For homework 3B, which is due Wednesday of this week, it looks as though chapter 5, Carnation and Newts. What is that? Well, just inside our textbook, there are problems at the back that are called carnations. Instead of a problem number, we got problem names and newts. And then in chapter 6, conservation and grades, the data sets in order are blooms for carnations, newts, conservation, and grades. So that should be fine. Do that and turn that in soon. If I were to, however, go back. Yeah. What I want to sort of do, unless there's any questions, move forward into new content. Okay, so let's do this and let's do this. And let's talk about designing an experiment. Okay. And maybe yeah, let's start with this. So, suppose we want to design an experiment to determine, and this is maybe in the context of a study on grapevines. In particular, we would like to have grapevines that will have the least water usage. They will have the best health overall, and they'll have the optimal size of the grape berry at harvest time. Okay. So there's some sort of a belief of there's the optimal output and that we can measure it. It could be maybe you care about pH or the size of the berries, or maybe care about phenolactic compounds inside the grapes. There's a lot of different things that we might care about. Okay. The amount of water we would use would be something we would care about, but that's more of a treatment characteristic. Okay. And the one primary way we in California seem to want to deal with keeping grapevines healthy is to make sure there's something right near the grapevine row right along where the grape plants are. It doesn't matter if we walk down a path or you drive a tractor, through a path, that's fine. But the key is right along the area where the grapevines are, you would say, I would love to see some grass there, or some sort of yarrow, or maybe some lupins. Lupins are cool because they fix nitrogen into the soil, or maybe just put some compost there. And what we want to do is we should consider the different sorts of treatments, the ways that we could treat these grapevines. And so list off a couple of treatments that seem plausible. So the treatments that we have in mind are, let's make this ink smaller. One is a cover crop, and I'll call that CC. Two would be compost. I'll put that as a C for compost, cover crop CC. Uh, let's go with three, both. And C plus CC. Okay. And then maybe a fourth could be the control group, and that's bear. And let's go with B for bear rather than C, because C we've already used for cover crop. I think the key is we got to try it out. We got to literally apply a cover crop to some portion of the field, compost to another portion. A third portion could be just, both of those, and then bear could be a fourth portion. Okay. Uh, in the context of experimental design, I would want to say we sometimes have to guard researchers about the difference between replication and pseudo-replication. What is a replication? Replication literally is if I do something to like a collection of plants, and then I measure that group of plants somehow. If I measure it multiple times, I might think there's more data than there really is. If I treat a whole row of vines all the same way, yeah, I don't get to measure every single individual plant and say, I've got 25 data points because I got 25 plants. You've got one data point effectively for the whole collection of all 25 plants. Literally, the way we treat an individual treatment group, a treatment unit, if I'm applying treatments to a whole row, that's a treatment unit. I have to have one data point per treatment unit. We'll see that in a later chapter, 8 or 9, where we're going to talk about this. But the key is if we treat something, you get one data point per treatment unless you're using special different rules. So what about randomization? Well, the reason you'd want to use randomization is you have this belief that if we were to take our field and we simply say the first 5 rows, the northern bits, if you will, get the cover crop, and then the next 5 rows get compost, then the third 5 rows get the both cover crop and compost, then the fourth group of 5 rows are bare. Well, what if there's this secular trend that in the northern part of the field, you end up with better soil for grapes? And in the southern part of the field, where we have bare soil, you also have the worst soil, even if you had treated it properly. If there's this trend across the different rows, yeah, you'd want to have randomization so that way each of the 4 treatments, the cover crop, the compost, both, and bare, all 4 of those treatment groups has the same chance of getting the good soil or the really poor soil. Random assignment, okay, avoids bias. What about this concept of blocking? Blocking is actually sort of a very normal way of thinking about things. Let's talk about maybe this more carefully in the context of the actual place where we did this experiment. And let's go with black. And this is up near Paso Robles, and I guess 46 here. That's where that highway is that heads from Paso Robles, PR over there, and then eventually over here, Bakersfield on the very eastern portion. Okay. And Estrella area is where we're talking. If you drive up north and you go to the water park, it's on the other side of 46 from the water park. You could look to the south and you see sort of a bluff well above the level of the highway, 40, 50 feet up. That's sort of the area we're talking about here. And these vines are in rows. There's a row, a vine row, yet another vine row, a fourth vine row, a fifth vine row, more and more vine rows, okay, as we sort of are going to the south. And there's an awful lot of them. So yes, you'd want to randomly assign treatments to the different, literally assign treatments to the different, if you will, the different rows. But we need to be aware of 2 other factors. One of them is you've got an underground river off to the east. Okay, it's literally heading north and then it heads to the west and ultimately heads into the Salinas River. So there's this river off to the north and east of where our vine rows are. And actually it's sort of close here, actually quite close. Okay. And then it's a little bit closer to Highway 46. And so sort of the area to the east has underground water. And even though these vines are sort of up some, 40 feet up, the funny thing about grapevines is if they're very old at all, they push their root systems down 30, 40, 50, 60, 70 feet. And so they could be off to the very eastern portion of this field, pretty darn irrigated. They've got a lot of water going on. So on the east side, okay, it's a one type of water condition. You'd expect the vines to grow differently, maybe better, maybe not as well. I don't know. Depends on what the type of grape is and other factors, but certainly east versus west matters. Okay. There's another factor, and that is the northern portion versus the southern portion of this field. In the northern portion, it's pretty much near the wind, which off the Salinas Valley often comes in from the west and the north. So it's, if you will, in the northern portion, we get windier. So we get windy and dry in that first quadrant or second quadrant, I guess, if we're doing trigonometry. We've got WD for windy and dry. I have an extra character here. Hold on. There we go. Windy and dry. Okay. And the lack of windy is calm and dry because you're on the west side, so you're dry, but you're in the southern portion, so you're calm. Okay. Windy, moist, and then calm and moist, if you will. These are four distinct portions of the field. And if I wanted to be really super careful, I would probably say we could do a better job. But we believe that these are other factors or other variables which would indeed impact the resulting characteristics of the grapes that are produced. Okay, yeah, literally the grapes we should have in our 1, 2, 3, 4 different blocks, if you will, block 1, block 2, block 3, and block IV, block 4. We're going to have these different characteristics because of just how dry and how windy it is. So no matter which treatment it is, I'm going to say the upper right quadrant, if you will, or block 4, if you will, is going to be systematically different than the second one, block 2, or systematically different than the first one or third, regardless of the treatment that we apply. And so how do we deal with blocking? What we'd like to do is design an experiment such that we have the 4 treatments distributed across the 4 blocks, such that we have the same number of treatments applied in each of the 4 blocks, one, and we do it at random. So I'm thinking if you are picking locations for the cover crop to occur, you randomly choose in block 1 of the locations to receive the cover crop. And then in block 2, you choose randomly one of the locations to receive a cover crop. In block 3 and in block 4, again, randomly choosing the location where you get the cover crop. Let's go for blue for compost. Compost is light blue. Randomly choose a compost blue. Randomly choose blue, randomly choose blue. And across this, we repeat the pattern across cover crop, compost, both, and bare. And then we repeat the process until we've filled up all of the different half rows. The right half, if you will, the half that's east of the, I guess, the left half, which is in the west, we'll take a whole row and apply a cover crop to a sort of half of a row. And then the other half of the row is going to get a different treatment. The way we do this, it really is to effectively say, if we apply to just one plant a cover crop, and then right next door we have to apply no treatment at all, we just kill the weeds, and then sort of that's it. And then a third one over is both of them, then another one with cover crop. If we apply to individual plants, it's too labor intensive. And so we're going to treat a whole half row at a time. Any questions about the way you could randomly assign treatments separately in each of these different blocks? Okay. So if that's the case, and I'm going to clear this, if we're able to assign treatments at random within each block, we're going to be able to sort of tackle the analysis pretty well. And the model that I would fit using Greek letters, not word equation at the moment just yet, is and let's go with the size of the grape. The size of an individual grape on an individual plant is based on, well, what is the average size of this variety of grapes? Then there is the effect of the treatment. So, yeah, there's an average. Okay, I'm sorry. I should have underlined the row below there. There is an effect on the treatment, of which, an effect on the mean, of being in a treatment group. There is an average and then a treatment, TTT, effect. But there's also a block effect, which we're going to say, we're going to call that beta. And for better or worse, block effect is sometimes termed beta. Please don't think of it as a slope. It just is which group are you in? Which block are you in? Upper left, upper right, lower left, lower right. And we believe that being in a block, there's some characteristic effect on the mean. Any of the individual half rows in that block will tend to be a little bit beta, higher or a little bit lower, depending on which block they're in, because of that. Then there's, of course, always the error in the trend around, I mean, it's the error in data points around the trend, if you will. So over here off to the left is what you'd expect. Okay. If indeed there were no errors, but individual grapes are sometimes higher or lower, larger or smaller than you'd expect them to be otherwise. So, in the context of this situation, it looks as though we've got these two categorical variables, A and B. The treatment effect, A, and B, the block effect. Let's talk about a situation where we see data much like that. Let me describe an experiment and pull up the data. Actually, it's sort of in crops and in particular in wine and vit within crops best. We have here information on the sugar content, Brix 3. I don't know why 3, but there's this number called Brix, and it's a way of measuring the sugar content in grape juice or in juice in general. And for the first individual plant is 21. For a second one, it's 22.4. So you get information about the sugar content. That's why. And it depends on, well, what above ground variant, okay, we have. And I'm going to call it clone. And clone should be categorical, uh, because it's individual clone. It's not a number. It's just what is the. We bought the clones out of a catalog. This student in fruit science, she said, okay, I just flipped open the catalog and someone says I should buy some 23s because they grow well around here. I should buy some 115s, some 667, and some 771s. And they're not great names, but they are different clonal variants. And 23 is the same genetically as every other 23 or every other 23 or every other 23. It's from the same plant. And this 771, it's genetically the same. And the above ground portion of a plant that we will call the clone here, or the scion, okay, has perhaps an impact on the sugar content. The below ground portion, a rootstock, well, okay, in fruit, let's talk fruit. Um, Depending on the type of fruit, but grapes is one of them. You might want to choose a below ground portion, the roots, if you will, that's disease resistant or matches the soil characteristics in your area, etc. And this student said, "Okay, boss, what should I buy for rootstocks for my experiment?" And the boss said, "Okay, buy some 10114s because they do well over here, some 110Rs." Rapidia Gloria, some 3309s, and some Schwartzman. And I don't know, I'm assuming that was named after Jason Schwartzman, the actor. That was supposed to be funny, but none of you laughed. Ha ha. We have these literally different rootstocks that could, probably won't, but could impact the response. And literally, the clone we believe likely will impact the response, but I don't know that either does. How would I do my analysis? Like before, we're just going to analyze fit model. This is just what we've been trained to do. And in that last section here, we'd say Brix, sugar content, depends on, well, clone. I'm going to put it first because I think that's the one that's likely to matter to me. But this other variable, the blocking variable of rootstock, we're willing to admit that across the rootstocks, there may be differences in the sugar content. And I don't really care about the exact effect of rootstock, but I want to say I want to study the clonal impact across a wide variety of reasonably used rootstocks in this area. So we're blocking because A, there could be an impact of the rootstock, and B, let's try out a variety of rootstocks just to see if the impact of clone is going to be the same across all of them, or maybe there's a difference in the impact between them. That's chapter 7. Hold off on that until later. I click run. That's just what we do. We run. And what we have here is, well, R squared for first thing. We're explaining 76% of the variability in the sugar content. Okay. Let's get down to our analysis of variance that says across either clonal variant with 4 types and thus 3 degrees of freedom, or rootstock with 5 variants, thus 4 degrees of freedom, across any one of those 7 parameters, if you will, 7 degrees of freedom, at least one of those terms, one of those effects is non-zero. MIP value says, no, we reject that. We believe at least one of the effects is non-zero. We reject the null of they're all zero. There is no effect of clone or of rootstock. We believe now instead that at least one of them doesn't have an impact. The model utility test, the analysis of variance for the whole model, basically says at least one of the terms matters. Check. We agree. Under parameter estimates, we'll look at that one later. Under effects test, we learned last time that is, well, controlling for the differences possibly across rootstocks, you would say there is a noticeable impact of which clone it is. Yes? Check. Controlling, allowing for differences between the 4 different clonal variants. Is there a noticeable difference across the 5 rootstocks? Yeah, I don't see one. So it seems like we've answered the question. Here's something that's sort of cool, though. In a properly designed experiment, we will often have what is termed balance. Okay. Balance. How do I describe this? Oh, for each of the treatment combinations, we have the exact same number of data points. Whereas we've got 4 different clonal variants, 5 different rootstocks, 20 different possible treatments between the rootstock and the clone. And if we have always the same, like there's one of these, and there's one of those, and one of those, across each of the 20 combinations, there's exactly one of each of the possibilities. We've got balance. Balance means you have the same number of observations, the same number of replications across every one of the treatment possibilities. A quick way of checking that would be maybe graphically. I'm going to use analyze fit y by x. This only works in situations where you have 2 explanatory variables. And let's, across the rootstocks, can I predict the clone? What I'm spotting here is there's exactly for each of the 1, 2, 3, 4, 5 rootstocks, each of the clonal variants occurs exactly once. We see sort of parallel stripes that are all the same in width. Or in the context of a contingency table from that earlier stat class, you have for 23 clone and 101 14 rootstock, there's exactly one occurrence. 115 clone, 101 14, one occurrence. We have for each of the 20 possibilities, we got one of each. Parallel stripes of equal width. We've got balance. And if you have balance, check. You have something called orthogonality that we'll talk about later. Orthogonality. It's your friend. Orthogonality is something you'd love to have in any experimental design, because if you have orthogonality, so balance gets you orthogonality, which gets you the good stuff. The good stuff is this. If I were to turn on my underestimates, my sequential tests, check it out. The sequential sums of squares is the same as my adjusted for both the first term and the second term. Well, of course, it's going to be for the second term. The second term is by definition the way we get the adjusted sums of squares. But I don't really then, when talking about clone anymore, I don't have to say controlling for the effect of rootstock. There's a noticeable difference across the clonal variants. I could say, is there a noticeable difference across the clonal variants? Yes, there is. I don't have to say, if I have orthogonality, I don't have to say controlling for the other variable. I don't have to say it. We like that feature. Okay, so what we're really doing is saying if there's another factor that you think matters, and if it's categorical, and if it's a design experiment, you typically are going to want to do this. Okay. Make sure you have balance in your blocking. The blocking really reduces SS error and therefore reduces mean square error. Okay. It also will tend to increase the F ratios. Check. We love that. Lowers the p-values. Again, we love that. Conceptually, what we're saying is if you do blocking, you're going to be more likely to see something as statistically noticeable than if you don't do the blocking. Okay. Any questions about that so far? Okay. So because this is a summer term, I don't really want to spend any time on this. It's also not really emphasized in our book. I will say, though, you can say, how efficient is the blocking? Literally, you could say, how much better off are we because we did the blocking? And we define that as relative efficiency. And if someone tells you a relative efficiency number, basically that's how many more data points you would need if you were to not bother with the blocking. Again, I'm sort of not mentioning this for the sake of what you need to know for the class, but rather so that way when someone talks about relative efficiency in a different context later on, you'd say, got it, I've heard of it. Okay, so one last thing. Let's talk about another way that you could have orthogonality, but lack perhaps balance. Okay, balance gives you orthogonality, which gives you adjusted and sequential subset squares matching. You could get orthogonality even if there's a lack of balance. Let's sketch out a situation where we would actually be likely to find that to be the case. Okay, so balance. So orthogonality without balance. And that's a W for without. So how could I get orthogonality even if I didn't have balance? Well, let's consider a situation where we've again where we again have those four different blocks, northeast, northwest, southeast, southwest. So blocks, 1, 2, 3, 4. And we've got our four treatments. There's mhm. So treatments, compost, cover crop, compost plus cover crop, and then both actually, hold on a second. Yeah, and then sorry, compost plus cover crop is both, and then um, bare grounds. So in each of these four situations, let's say you had a desire to have fewer cases of the bare ground and more cases of each of the other three. Okay. And what if you have a situation where you're going to go 1/3 overall, 1/3 for the compost, I mean, for the cover crop, because you think that one's going to be best. And then 1/6 of the data values are for each of the two variants on the cover crop. You think cover crop really matters. Okay. And you want to be able to compare it to bare ground pretty effectively. The comparisons between cover crop and compost or cover crop to cover crop plus compost, you care less about. Remember in the equation for the t-test, you have the standard error is equal to the root of mean square error times root of 1 over n plus 1 over n. Okay, if we have these two 1 over n terms and they correspond to the cover crop, okay, You might want that one to be a large value because we want to be effectively comparing the cover crop. You might want some of the treatments to have more precision than others. So you would want to have more of the data. So we're saying let's split the data into six groups overall. One-sixth of it would be getting just our compost. Two-sixths would be getting the cover crop. One-sixth would be getting the compost plus the cover crop, and then two-sixths. So one-sixth overall, two-sixths, one-sixth, two-sixths. And so for each time we assign a cover crop, I mean a compost, you're going to do two cover crop assignments, and then one that gets the cover crop and the compost, and then two that get bare soil. Okay. In a situation like this, you would have orthogonality without balance. Again, balance means the same number of treatment replications for each of the treatment combinations. There's 16 treatment combinations. We're saying we don't want that, but we still get the orthogonality. And the reason this makes sense, and if you think about it, orthogonality boils down to if I tell you one of the explanatory factors levels, does that change up your bets at all about the level of the other explanatory factors? Suppose I tell you you're working in block one. You still think it's a one-sixth, two-sixths, one-sixth, two-sixths is the rate of occurrence of each of these different treatments. Or what if I tell you you're working in block three? It's still one-sixth, two-sixths, one-sixth, and two-sixths as the rate of occurrence of each of those different treatments. So the same rate of occurrence across the four different treatments, regardless of which block you're in, still gets your orthogonality. You might be lacking balance, but the reason you want to do that is you care more about certain comparisons than others. And the comparisons that you care about, you want a small standard error. So you want large values for n in the comparisons you care most about. And if you don't care about a particular treatment all that much, you could go with fewer data points as long as it's consistently fewer, proportionally fewer across all of the differing blocks. Any questions about that? Okay, so I'm going to sort of shut this down. I'm going to stop the share and maybe I'll do that first and stop the share. And I'm going to sort of close out by saying, in terms of the lab groups for this week, basically there weren't a whole lot in the way of requests. Okay, and the requests that I did try to honor, okay, I did it in a way such that no one else's requests were dishonored. And if you find that this set of groups for this week, and I'm not sure who's paired up with who, but it is a little bit different from last week and different from the first week as well. Not for every one of you will you be matched up with completely different group, but with someone that you maybe have not met before. The reason we did this is just to make sure that it works out, but I suspect that unless one of you or more comes to me and says, no, 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 you misheard, misunderstood, or we didn't tell you, but now we strongly want you to believe the following. Unless I hear a compelling reason to switch up groups again, we're going to stick with week three groups into from 3 to 4 into week 5. That is my hope. That is my plan. And we'll find out if that's what you all think. But you've got groups for this week. And I'm going to, unless you guys have questions, I'm going to stop the recording and say, go and do with the lab. Okay, so I'm going to stop the recording and let you know office hours start in right around 20 minutes, and we'll hopefully see you then. Bye-bye.
Thank you.